Okay. This is kind of a little bit of a expanded presentation from fourth day. It is designed to get people interested in the AI community. They're very interested in hardware AI. And we have over 3,000 people, actually 3,300 people in our AI and robotics groups. So I'm going to be posting this on the groups. And so I am going to be going back and, kind of reviewing a few things here. First off about me, I'm a senior staff engineer for a small company that we primarily design space systems for Goddard and JPL. I'm working on a brand new design for the space community where they can get off-the-shelf space hardware at a really inexpensive price. I designed the NASA Arcanaut 1 computer, which 3D prints a 10-meter beam in space. And I was founder of Space Tech Inc. back in 1979. We worked with medical imaging computers and systems. I was also the founder of Angeles Research Corp, and I built intelligent robots. Whiskers, some people know about. There's over 50,000 students per year for probably over 7 years that were taking robotics courses in junior high and high school laboratories. I also built the first military man-packable robot for the U.S. Special Forces. And because my interest is in intelligence, back in those days, I developed a triune OS that actually emulates the triune brain, which is a very biological. That's the way that we work. That's a different video. So I'm going to show you some of the machines that I worked on. This is Lockheed Martin's Mule, and it was multi-functional, whatever. It's a 2.5-ton machine. It has 6 kilowatts, brushless motors on each arm. Those arms you see, they articulate. They'll actually do a 360, and these things will climb over the median on a freeway. It was fully autonomous. It had 6 Cyclone FPGAs with 2 32-bit processors. This is Altera, and I was the lead engineer on the computer, and I actually took it over from someone who designed it and got it working. This is Arcanaut 1. It's fully autonomous. Like I said, it's a 10-meter lattice beam. It was supposed to launch this year. NASA did cancel the program because they couldn't find people that wanted to 3D print in space. So very sad it's not going to launch. But so NASA has this machine sitting. They own it, and it does work. These are a bunch of the different robots that I designed back in Angeles Research Corp days. And the upper left was a new military robot. This actually, you see these 2 knobs here. You take those 2 knobs off, and you can remove the treads. So you could fit this in probably 2 soldiers' backpacks. This is Intruder Robot. And I sold one to actually the CIA, and they used it on a real mission. That was Southwest Technical Research. That was a funny story. And then this is the advanced robot. This is Whiskers. I actually shipped them with a clear top so the kids could see inside and see the electronics. All through-hole parts. But it did use the Triune OS, and you talk to it in English. Forward 10 feet stop is real code. I also built an automated guided vehicle for a science museum in Georgia, and there was a belt on the top. It would go from one conveyor, and it had light beams. When the box came in, it would detect it. It would pull the box on, and then it'd take off. You can change it. Its its path by just changing the white tape on the ground. It also has a collision avoidance sensor, so if someone walked in front of it, it would stop and wait till they pass. And this is a kid I was trying to get as things were winding down with whiskers and people started going into Legos labs. I created a kind of a erector set sort of robot, but that didn't take off. I did give a talk at an IoT summit of things. So one of the things in researching IoT, it's really encompasses almost everything when you think about it. It's from personal robots, surveillance robots, cell phones is IoT, drones are IoT, smartwatches, things like 3D printers and hobby bots. So IoT is really a massive environment, which Forth is just perfect for. So here you can see, sorry about that. On LinkedIn, I started a group about 6 months ago called AI and Robotics Group. There's over 3,000 members today. You'll notice that there's 15,000 post views. And when I put an article on here, I typically get about 1,000 post views. And I will put this presentation on there for people that are interested in a new way to integrate AI and hardware. We also have a Facebook page, and we have 356 members. We kind of get a lot more technical in this group because there's a lot of Forth people in this group. Dr. Chang Lee, he worked very closely with Dr. Ting, and he's continuing on with Dr. Ting's work, and he's got some very interesting things. I would encourage everybody to join this group. So now I'm going to talk a little bit about the Core 1 technology that I'm developing. And Dimitri, of course, is one of the co-developers on it. And we look at it as being building the next generation Forth system and programmable chatbot, you might say, in FPGA, so in hardware. A little background on Forth. Forth was invented in 1963 by Charles Moore, and which is about the same time that AT&T designed C. And up until I would say the mid-90s, Forth was the preferred language for embedded systems. C took over because Forth wasn't taught in academia and wasn't promoted by the large corporations. Forth has used the chat box interface since its very beginning. It's always been a chat box. So you typically would have a serial port and a simple terminal program running in your computer with a serial cable. And that's how you talk to Forth. And that's how you download source code. And that's how you test things. So we had the chat box interface since 1963. The outer interpreter promotes simple testing and debugging. In the C world, they use Java and all these more complicated things, Python. Forth has been doing this for a very long time, 60 years, I guess, right? Forth has a simple incremental compiler. So you can basically add words. Words are functions in Forth. Very simply, you can interactively type them in, or you can edit your source code in a notepad document and download it and compile it. But the important thing is this incremental compiler. So you don't have to compile the entire thing and create a binary blob and then JTAG your processor. Forth is a virtual machine and easily implemented in silicon on a chip. Forth is a meta language. It's easy to implement other languages in Forth. One could write a C compiler in Forth. I don't think anyone's ever done that, but there's Lisp has been written in Forth, Smalltalk, Pascal, a lot of things. Dr. Ting was working with Python parsing strings, and during one of his talks, is during COVID, he actually decoded the COVID-19 genetics. And he said Forth was, when he wrote the same algorithm in Forth, is 60 times faster than Python. Why not use C? It's not interactive unless you use a derivative like Java or Python. It's a very complex compiler. The compiler is amazingly complex, and it requires a powerful computer. An interesting little side note is if you look at the interim language that the C compiler creates before it actually creates the final opcodes, you'll see swap drop. You'll basically see a lot of Forth words in there, which I thought was kind of interesting when I explored that. With C, you have to compile an entire application if you change one line of code. Of course, what they did was they created DLLs, dynamic link libraries, to try to get around this problem. But it's still a problem. If you change one line of code, you have to compile your entire application, which you don't do in Forth. You only compile the function you changed. And then you have to JTAG the binary into your CPU. So it's very cumbersome updating your software in C. You need a lot more memory and processing power to run C programs, typically, a lot more. Reprogramming on the same machine requires an OS or Linux. You need, some sort of OS, to have a C compiler and editor and all that stuff, where you don't need any of that stuff. Forth and hardware. Forth is really not a language, it's a virtual machine. Forth is really a chip design. And, we talk about it as a language quite a bit, but it's really a virtual machine that you can implement on any processor. Almost every processor ever made, somebody wrote a Forth for it because it's so easy to write Forth in assembly language or even C. One of the talks that Chuck was given during his Forth Day, he said he discovered Forth while working on the Kit Peak telescope. Chuck, in early 1960s, was the programmer for the Kit Peak telescope. And he was writing everything in assembler. And he started, instead of doing gotos, he started using go subs. And he started seeing a pattern of a language, and that language was Forth. Forth, because it uses a stack, it has a mechanism to pass parameters in hardware. And that is why one of the reasons that it is the ideal hardware language, hardware machine. So Chuck went on during the 80s and the 90s to literally, put the Forth engine on chips. And here's a picture of a lot of the different Forths. And the NC4000, the Shaboom, the RTX 2000. And the RTX 2000 found a big niche in space systems because it was so radiation hardened that Harris Semiconductor actually bought the rights to it and came out with RTX 2010 and wrote a C compiler for it. But it's literally a Forth engine, and it's been on all kinds of space missions and with very close to zero failure rates. And then Green Arrays, another company that Chuck Moore founded, put 144 small Forth 18-bit wide computers on a chip. And the amazing thing is he wrote his own language, you call it color Forth, to design the chip itself rather than using tools. And I think it took him like 5 years. But anyway, it's a fascinating story. And if you go to Ultra Technology /chips, you can see it. So I put an FPGA in there because my feeling is Forth today is its ideal application as an FPGAs, which is what we're talking about today. General purpose computers versus a Core 1. So I'm using this very powerful laptop. It's an IMS, and it is a gaming laptop. It has 8 cores. It's got 3,500 GPUs. And when I'm doing, I'm an electrical engineer, and I use a program called KiCad or Altium. And when I use those programs, I can see the computer slow down. I click on something and I do an operation, and it'll take seconds on a machine that's supposed to be 2.6 gigahertz and 16 gigs of RAM. So, today's computers are just really slow and very inefficient. So I was curious about how many opcodes a typical, like say Windows. What does Windows use? So the estimate's about 5 to 10% of the CPU's instruction set is utilized on an average computer. Only 5 to 10%. Today's computers require a general purpose operating system, slowing program execution. They're doing, if you look at Windows, it's got 4,000 threads running. What is it doing when I'm just, I'm clicking, I'm viewing things on the screen, I'm doing searches, but it still has 4,000 tasks running in the background. They're high power consumption and low efficiency. With the Core 1, you implement only the opcodes you need. You can literally comment out the opcodes you don't want and synthesize the system and utilize 95% of the opcodes. The Core 1 FPGA benefits is fully programmable. It's 32 bits standard. It could be 64, it could be 128, it could be some weird number like 73. Just one parameter changes the data path width. And it's a computer on a single chip. It includes an outer interpreter on chip, which is basically a chat box interface in silicon. It has an incremental compiler on chip. It's built on the Forth virtual machine. You send source code through the terminal interface. That's how you program it. You can also interactively test your codes. You can even test the opcodes interactively. So one of the core things you do is you create your own opcodes that would normally be functions in software. You create the opcodes. They are generated in silicon and run at 200 million instructions per second. So we can move application software and code into hardware using the system. There's no external development tools required for Forth code. The future is to build a very high-level natural language on top of Forth. Forth core computer features. You can microcode Forth programs and words in boot ROM, and the boot ROM is internal to the FPGA. Again, the FPGA, has its configuration memory, and you can literally microcode Forth programs. So microcoding is like, programming in assembler, for example. Core 1 extensions or opcodes can be very complex. They can take as many cycles as you need. So if you're going to do a hash 256 opcode, it will complete the entire process, and you don't have to worry about it taking too long. What we do is we stretch. We give you as many cycles as you need. So if you use 100 cycles out of 250 million, that's not a lot of time. It'll look instantaneous, but so we stall the processor, and it makes coding extremely easier. One of the tricks about FPGAs is people start a project, they say, I want my computer to run at 50 megahertz. So that means all opcodes, if my other goal is I want them to execute in one cycle, then I have a time constraint, right? So with this, it's automatically extends the the number of clocks until your code finishes. So it makes it really easy to write very complicated opcodes. So that's what the C is in Core 1. It's CISC over RISC engine. The RISC engine is a fourth engine. The words that you write are in system Verilog, and they execute at the speed of silicon, like I said before, 200 million operations per second. We can, because fourth is so easily extensible, we can steal or borrow high-level concepts from other popular languages. For example, we could implement PyTorch, on the system. The computer grows as FPGA technology grows easily. So you get more powerful, cheaper FPGAs. You just move your code over there, you synthesize it, you're up and running on the new hardware. You can network multiple 32-bit engines together inside the same chip or externally. You can store source code in Flash or on disk and compile on the fly as needed. Can't do that in C. Take SRAM snapshots and store them in Flash or SD card. So imagine you have a session using the fourth computer, and you have a bunch of variables and things defined. Well, you can use a save snapshot word. The entire snapshot would be stored in the flash memory, and then the next time you power up, you have the exact same system the way you left it. Wouldn't it be nice to have instant on computers? Core 1 development goals. We want to develop a vast open source user community in the AI community. So we have a GitHub, which we've already set up, and people could share their opcodes. So they can test out their opcodes, they can share them with other people. You could have thousands of opcodes in different categories, pre-tested, and just copy paste them into your machine, and now you just added a new opcode. That's the future. One of the things I'm very interested in is AI. So Llama, which is an open source data set, they have a 7 billion parameter data set, and you could load it into the flash memory I have on my current Core 1 AI Playground board. It's only 33 megabytes in size. Now we have to build the inference engine on top of it to run these, and I'll talk about that a little bit later. So the benefits, of course, is create your own complex opcodes in system Verilog. You can share opcodes on GitHub. Opcodes run at the speed of silicon, greater than 200 million operations per second. You, using system Verilog, create thousands of parallel processes on the same FPGA that the fourth is on. You can create parallel processing device drivers for peripherals. You don't need a bunch of interrupts like you do on CPUs. What you do is you create system Verilog code that operates something like, let's say, motors, or the UART or whatever, and they work in parallel, and so they pre-process all the data coming in, like say from ADCs or outputs to DAC or outputs to HDMI, and so it's all pre-processed, and then you just simply use shared registers, and the fourth computer can send and receive data to these parallel processing device drivers. You can send source code over remote internet or RF link to compile directly on the chip. So this system, we're using fourth and system Verilog. So system Verilog, if you know C, you're 80% there. You know system Verilog. So system Verilog syntax is C syntax. Although there are some differences that you have to learn, but on this system, it'll make it easy because you can create an opcode and you synthesize it and you program your FPGA, and now you can interactively test that opcode. You could give it different data, and you can test out the results to check all of the use cases and make sure that your code is working properly. So by using System Verilog with Forth, you're able to write or create an embedded system that is intelligent and extremely fast. It would smoke any laptop computer or desktop computer for a custom application. So you have easy programming, you have a natural language processor, interpreter, front end, incremental compiler, extensible high-level language, chip processing and System Verilog. Code in System Verilog actually becomes circuitry in the chip. We call it fabric in FPGA world. All processes that are created in fabric in System Verilog run in parallel. And we're talking, again, 200 million operations per second. You can build massively parallel systems, which I'll get into in a minute. Fourth is a user interface or chat box. System Verilog, think of it as the assembler. You want to program all device drivers in System Verilog. All System Verilog, as I said before, run at over 200 million operations per second. All System Verilog processes run in parallel. FPGAs can run thousands of parallel processes concurrently. Multitasking is supported in Forth, but it's really multi-processing is the key for using an FPGA. So here's an example of a typical setup with the Core 1 board. And you would have an optional laptop. We do include a 32-bit ESP32 computer running Forth as well. And this is your interface to both Bluetooth and the internet. So the Forth computer could ask the ESP32 to go search for something, or maybe go ask Claude or Bard or ChatGPT for some data, and it could get it back through this interface. The Forth computer can have, actually it's up to 512 by 36, but it's 3 nanosecond SRAM. So the FPGA basically is running at the same speed, so our external RAM is actually as fast as the silicon. Now this is way, way faster than DDR anything, DDR4 or 5, whatever. 3 nanoseconds, and it's totally deterministic. With DDR, if you get a page hit, it can be 20 nanoseconds. If you get a page miss in the memory, it could be up to 70 nanoseconds or even longer to get the data. So this is going to be this system is going to scream. So here's an example how I might use some Core ones. So the Forth computer has the incremental compiler and the interpreter built in. That's why I call it a Forth computer. The Core 1 only runs, macro code. So you macro code these guys. Of course, this takes more LUTs than these guys. The Core 1 is probably 1,200 to 1,500 LUTs, and you can macro code it and create like a display driver, or maybe controlling a flash memory, controlling an SD card. So imagine a Forth computer tells this guy to create a box and load an image into that box, and then the next line of code says go look in Flash for some source code. I need to incrementally compile a new word in my in my stored dictionary libraries. At the same time, I'm looking for data on my SD card. And all of those processes are running at 200 million operations per second. We have a PS2 keyboard interface. And like I said, you could, in theory, code directly on the display. It's a small display, though. On the first board, it's only 4 inches diagonal. So you might want to use a 232 in the beginning. Later on, a future board, we can put a full display on it, like this one. Now, okay, so there's all this code out there for AI. You know, do I really have to write everything over and forth? No. So what you can do is you can put a RISC-V inside the FPGA and have it as a coprocessor to the fourth computer. So you can use C, C++, PyTorch, Python. Now, in this case, we'd want to put DDR RAM, which I do not have on the first board. It would be a next generation board because the RISC-V is going to need its own dedicated memory. Although you can utilize the SRAM for the RISC on the current board, and you'd be limited. The current board has 64 by 32 bits, which can be expanded up to 256 by 32 bits on the current board if you want to experiment with this system. So it's pretty much the same thing. So let's take a look at when you write code for computers today. You know, we called it back in the day Wintel, Apple, Linux. So you have the sequential machine. It only does one thing at a time. It only operates one opcode at a time, right? That's the model. This is sequential processing. You've got applications sitting on top of an OS, sitting on top of hardware. Very complicated. That's what your laptops work. Yeah, they could have multiple cores, but do a Control-Delete, look under tasks, and you'll see that most everything's running on the first core, and the other cores aren't being used. So we haven't figured out how to really distribute, programs today on multi-core computers. On a fourth machine, you have massively parallelism, and you can have 2,000 processors on a single FPGA, and you can network FPGAs together to basically create any size computer that you want. You can make a desktop supercomputer, which actually had penciled out a design for somebody. So a massively parallel computer might look something like this. You have the fourth computer, and that's the interface to the user. Now, here's an example of using an FPGA as a silicon neural network. So each neuron would be running at 250 megahertz, all in parallel. And you can make it, X amount of neurons deep. And this is a massively parallel processing machine. This is what it is you can do with an FPGA-based computer. You can't do this with a laptop. Core 1A AI Playground board. So I've designed this board. I'm having some trouble bringing it up. That's why you haven't seen it yet. I'm probably going to have to do another board spin to fix everything. I've spent about $2,500 on it already. I probably need to spend another $1,500. But anyway, I got to get it done. The touch screen plugs into this connector over here. You can have a daughter card that plugs into the bottom. You could make this a stacking connector, and you could have multiple I/O cards. So, for example, to make a Whiskers 2 robot using this system, you'd have a single multi-function daughter card that would do all the motor control, all the sonar, and all the light, all the sensors and everything on a single board. electronic compass and all that. You can also plug shields into it, and you can see the board there. And these are the shield connectors. They should be receptacles rather than the pin version. That's actually the board there. The idea is to demonstrate the core AI technology, encourage early adopters, to build a community of developers, and benchmark some of these massively computer ideas versus a PC. So this is basically what you have on the board. The standard board would have a 25,000 LUT. The current full fourth computer, which includes actually pulse width modulation and some other features, is 2,300 LUTs. And this is 25,000 LUTs will be the standard board. I'm going to have a advanced board with an 85K LUT, FPGA, and 512 of high-speed SRAM. That would be a really powerful board. So, this is kind of some of the things we can develop, explore, define your own functions as opcodes, as I said before. Is to experiment with AI machine learning, neural networks, expert systems, implementing other languages, Lisp, Smalltalk, Prolog, Python can be implemented. Use the Core 1 processors for top level for all these different functions. Create input and output, and semaphore registers for the fourth engine to talk to these different other subsystems. So conclusion benefits, build high performance, low cost, intelligent embedded systems. That's the whole focus. Research novel fourth and other types of computer architectures. You could create architectures of dozens of different processors, 16-bit, 32-bit, all networked on an FPGA, running Core 1 cores. And so it'd be very interesting to see what people would do with that. Research develop AI on top of fourth. We want to add high-level constructs to fourth, like enum, string, struct, which we use crate does, some magic words in fourth. Easy way for beginners to learn about FPGAs. Normally, the whole process, you have to define a lot. There's a lot of restrictions, requirements in the source code to get an FPGA working for the first time. When they can start with our source code for the Core 1, they can simply start creating their own opcode and interactively testing it. So it'll actually allow people to learn system Verilog a lot easier than today. Obviously, using the serial port and fourth to debug system Verilog processes. This still fits in a $5 FPGA. If you wanted a single fourth computer inside an FPGA and play with the system, it's a controller designed for intelligent machines and robots. So this is kind of talked about most of this stuff before. Some different. So what it's showing is different. You can experiment with different architectures very easily with this. You could have a Prolog engine. You can have an expert system engine right on chip that could be running in parallel to the fourth engine, as an example. Here's a real example of defining plus in system Verilog. So the first thing we do is we set the busy flag true. And that means you don't have to worry about clock cycles. And then we're going to, because plus is going to consume a value off the stack and leave one value, we're going to decrement the data stack pointer. And one line of code right here is plus in fourth. Data stack, your current dictionary pointer equals the current one plus the second one on the stack. And now, so that means this will be replaced with these two items that are added together, busy, flag, false. How hard is that to code? It's really easy. Here's an example of massive parallelism. So System Verilog has a special word, function called generate. What generate does is you see it says I for 1,000. So this will create 1,000 of these neurons that are defined in here. And you notice there's an I. So it'll create a register from 0 to 1,000. So it's creating all of these neurons. And then you are going to need a different algorithm to connect them all to an output. But anyway, I just wanted to show you the power of this system. This is how you create 1,000 neurons, or they could be coprocessors. These could be, doing something else, not a neural network. These could be doing some sort of calculation. It could be doing, adding two things, 1,000, maybe you have 1,000 items, and you want to add them to 1,000 other items. You could do it right in here, and you would create that, and you would create 1,000 different processes on the FPGA. One of the things I'm interested in is what they're finding with these large language models. So Llama 70B is a very large language model that competes with ChatGPT-4. What they're finding is if you use a smaller data set, so the $7 billion 7 billion parameter data set version of Llama is actually quite small. It's only 33 megabytes, which can sit inside of a flash memory. What they're doing is do a search on large language models fine-tuning. And what they're doing is they're using the 7B data set as basically the engine that creates the AI intelligence. And then they're training, you train it with your data, and it fine-tunes it so that it responds to your data. Well, that's what we want to do with robots, right? So starting with the 7B model and then adding fine-tuning to it, we can use the same mechanism that ChatGPT-4 uses inside of our FPGA, inside of our robot, and make it smarter. Now, this is, this ain't going to happen tomorrow, but this is totally doable. And like I said, we could add a RISC coprocessor, so you could use PyTorch coding. So I just took a screenshot of the actual file. You see it's 33 megabytes. Oh, I'm sorry, this is a 70B. Oh yeah, so anyway, it's about 100 megabytes, I guess. So what I really want to do longer term is I want to talk to this guy. I want to talk to this machine, just like Spock talked to the computer. You've always been able to type things to forth and talk to the computer using text. That's been since day one. That's been a chatbot. Forth was the first chatbot. I did a little experiment when I was in robotics and endless research in the late 90s. I put a voice to text card inside my PC, and it was a big card. And it would, you'd hook up a microphone, you talk to it, it'd output text. And I used that as the input to Forth, and it worked just fine. You can buy boards now that cost under 50 bucks that do voice to text. So you could take one of those boards and you could hook it up to our machine, and you could use voice. And you could program in voice. So when I designed my robots, I didn't want a robot just ran programs, short circuit. I wanted a robot that made up its own decisions based on goals and behaviors and instincts. I'm not going to get into the triune brain very heavily right now, but the triune brain actually emulates the way the human brain works, and that will be integrated into the Core 1 because the multitasker is a lot better than a typical RTOS. So the triune OS in silicon, the cerebral cortex is the outer layer of the brain, folds under the skull. It's your decision-making, analysis, and dreaming. So that's actually, in my triune OS, that's your outer interpreter of the fourth engine is this. The limbic system is a gray matter found in the center of the brain. That's your hunger, fear, and feelings. So that's what I call the behavior level. You create behaviors, you prioritize them, put them on the behavior task list, and they automatically will be executed when the robot gets into that situation. And the brainstem is a brainstem connected to the spinal cord in your nervous system, and that controls critical responses and instinctive behavior. So this is kind of a block diagram how this works. This dotted line means this is a foreground task. This is your fourth interpreter compiler sits up here. Your tasks and behaviors sit here, and they look at different things, different data in the system. And when the data lines up for a particular task, that task fires. It's cooperative between these two. So when a behavior takes control, the goal stops whatever it's doing until the behavior terminates. Now the instinct level works in the background all the time, so it's not interrupted, and it creates different flags from the sensors and the motors and things, and they go up and they are looked at in the behavior level. If there's some certain sensor conditions might create a behavior. LLM, OS, AI, hardware architecture. So this might be, how an LLM might be implemented. Okay, as I told you before, I'm in the space business. What if you had 100 robots assembling something maybe out at Pluto, and the low-speed data link, which is about 750 bytes per second for NASA's deep space? Are you really going to send a 300 megabyte binary blob of that low-speed link? No. If you use the Core 1 inside a space-rated FPGA, all you would do is send 80. Maybe you only need 80 characters of source code that you upload the link, and the spacecraft would parse it, incrementally compile it, and it would switch to the new function in a clock cycle. Now, if you're updating a binary blob in an FPGA in space, that spacecraft is down for minutes, and it's not under control. You don't know what's going to happen. So I think at some point we need to get the Core 1 in space. These are kind of some of the applications I talked about in my talk in the IoT. This is a handicap assistance robot. It's a prototype that I built. So we want to make a personal computer really a personal assistant, right? I can't tell you, it boggles my mind that Windows 11 today crashes. It's ridiculous. Anyone can program personal assistants using voice. It uses very little power. it could be powered by a solar cell, maybe a couple of them. It can be small as a phone or a tablet. It communicates using voice, program using English. Even children can program it once they learn English. So maybe a 7 or 8-year-old. I just ran across this last week. I think it's in the step in the right direction. They're trying to make basically a personal AI assistant. Costs $199, but this is kind of where I think I want to go to. Of course, it's not open source or anything, and you can't really. Well, I don't know. It could be. Go check it out. But the point is, I want to build something that has a lot of intelligence that people can modify. And so what I'm doing right now, I kind of set aside bringing the board up. I'm using this board here. I have our Core 1 system is running on this computer. So over the next month, I'll be working with this, and I'll give a demonstration next month at SC Fig on what I come up with and get some things working. So I want to get to the point where Dimitri gave us, the live demo where he was controlling some LEDs, and then I've added a bunch of different opcodes to it. So that is the end of my talk. Everybody awake out there?
I'm awake.
Thanks, Don.
Thanks, Don. Any questions or comments? I wanted to say that there's at least one YouTube video and maybe a Wikipedia stub on the XM1219 Mule armed robot. So have a look.
Don, I will say, of course, I'm coming from bringing APL, which is intrinsically parallel notation. It has to be understood that it is. And the other thing is, I watched this long interview with Nicholas Wirth, who just died, and talked about all of these programs, languages, and so forth. And one of the things, actually, because he was developing his languages about the same time that Forth and APL were creating, he mentioned neither of them. And one of the things, actually, in watching his talk that struck me was that he was coming from this notion of big programs, of Algol and, Fortran and Algol, and Chuck was off here on the side, and forget this notion of making a massive program. You make a word.
Send me a link, would you?
And I think it's on my daily blog, which is linked on my site, which is updated in Cozy Forth. But one of the other comments, but I mean, really, people should go and check Dialog APL is big traditional, and they're looking for programmers. But an APL programmer, you have to, in a sense, be able to think parallel. You have to be able to think it, and you'll learn how to do that. I mean, it's evolved from matrix algebra and so forth. So, and generalized, and now, particularly after a couple of iterations in Cozy, it's incredibly simplified down to the fact that the quote in Forth gives you the word, the address of the next word, so you can pass that as a parameter to what an APL would be called an operator, and say, essentially, do this on everything. So, it just, in any case, the one final comment I'd like to make is when you're talking about, I don't know whether I really like this notion of calling an interface a chat box, but one of the things about both Forth and APL, man, I couldn't program if I could not just write down a sentence and have it execute. And this was one of the things, and these were both around the same times when all the big stuff was going on with algol and all of that. You had the creation of the APL workspace, where you could just write down a line and hit return, and it would do it. And that line could be, computations which were up to the capability of the resources that you had. And again, A plus B means you add the corresponding elements of A to B, or in COSI, A, B plus, But that's the thing. It's intrinsically, something like plus applies to all the items in your structures. Anyway, enough of a blurb for that. But there's really, I've looked at a purpose of going, creating APL, evolving APL in Forth, is to go from the arrays, the conceptual arrays in which these algorithms are written, to the silicon arrays in which they're mapped. And so there really is, we gotta connect the layers in this sandwich. We got the top and the bottom, and definitely there's a lot of jam that has to go into mixing them.
Well, somebody like yourself just sit down with this system and create an APL engine.
All right. Thank you, Don.
Yeah, cracking.
Maybe continue after the recorder's off, if Don is willing to hang around and converse for a little bit more.
Absolutely.
Got another engagement, so I have to bail pretty soon. Brad, hello, Brad. Can you do the screenshot for the meeting notes?
I will take it now. So everyone say cheese. All right.
Thank you so much. All right, we'll see you next month. Thank you to the speakers. Thank you for those of you who are here. Thank you for signing up on MeetUp and registering your attendance. You can do that after the fact, by the way, that you were here. Also, go to YouTube and view our videos and like and comment and do all the YouTube stuff. It helps our numbers. Thank you again, and see you next month. Bye.
All right. See you next month. I'll stick around if people want to talk.